Welcome back. So we will now discuss what we call direction cosines. Still dealing with the Cartesian coordinate system or the rectangular coordinate system. What do you mean by the what do we call this now? Direction cosines of a vector. So and how does it help us to obtain, for instance, the angle between two vectors? Okay, direction cosines. So look at this now in the two-dimensional case. So let's consider the two-dimensional case first. We have this as our x-axis and this as our y-axis. Let's try to have something that looks straight. Okay, so now if we have a vector in these in two dimensions now, so let's see. Now we have drawn vectors to, for instance, always emanate from the origin. That is not the general case. I mean, it is not always so. So you can have a vector, for instance, that is directed this way. Don't be embarrassed by that. If you have a vector that is directed this way, for instance, it is still in two dimensions. So for you to get the x component, you just treat it as though this was emanating from the origin, and you extend a line that is parallel to the x-axis, extend the line from this also that is parallel to the y-axis, and then you go this way. So this will tell you that it has an x component that is directed this way and a y component that is directed down. So that the sum of this and this, okay, which are of course these are at 90 degrees to each other, will give us this. Okay, so the x component of this is directed like this, the y component is directed this way. So we can have vectors generally that are not emanating from the origin or not pass through the origin. They can be located anywhere in the plane, but anywhere they're located, you can always write them this way. And of course, for each of them, we can write them now in terms of vectors I and j as well. So that is that about that. But what do you mean by direction cosines? So we know that this is some vector that is in the first quadrant. So to speak, by first quadrant to mean this portion of the coordinate system. This is the second quadrant. This is the third quadrant. This is the fourth quadrant. Now, we can have a vector that is not directed like this. So we can imagine that you have some vector that is directed this way, or some vector that is directed this way, or some other vector that is directed this way. So it's as though there is only one direction you can have, or all of them will always be in this manner. No, 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 no. So for each of them, you can talk about the direction cosines. That's is simply cosine. I mean cosine from trigonometry, sine, cosine, and tangent. Okay, that's what we are really dealing with here. It has to do with the angle that the particular vector makes with the coordinate directions. So the angle it makes with the x-axis, for instance, we can call that theta x. Okay, so we can also call this alpha, beta, and gamma. Anyhow you want to call it is fine, just notation. So I want to call it alpha now for consistency. So we say this is the angle that it makes with the x-axis. We're calling it angle alpha. Then we also know that it will make some angle with the y-axis, and then we can call that beta. So these angles tell us the direction cosines of the vector. So if this is some vector p and it makes an angle alpha with the x-axis, so what will be the x component of vector p? So we already know how to get x component and y components. We extend from this a line parallel to the y-axis. So where it meets the x-axis will give us where the x component is, and we extend the line parallel to the x-axis. We go this way, this way, this way. So this way it meets the y-axis. This will tell us where the y component is. So this is the components. I mean the magnitude of the y component will be given by this length. The magnitude of the x component will be given by this length. And of course, by the time you consider that this is a right angle triangle, and you know that for the trigonometric ratios, sine, cosine, and tangent, we say that we use the acronym SOHCAHTOA to relate the trigonometric ratios and the sides of a right angle triangle. So we say that the sine is opposite over hypotenuse Cos is adjacent over hypotenuse, tan is opposite over adjacent. So cos is what we are interested in here. So you should observe something here that if we're interested in the x component, for instance, this is the x component, the length of the x component will be from this point to this point. This is the magnitude of the vector itself. So the length from here to here is p. So the x component, if we're calling it a still, then is given by this. So how is p related to a? So looking at this, we see that a is adjacent to this angle. I mean, this is angle alpha. Opposite of angle alpha is this side. Hypotenuse is the longest side, which is the side opposite the right angle. So this is the right angle. Opposite the right angle is this length. So how you know the side that is opposite an angle is the side that is not connected to that angle. It's as simple as that. So this is angle alpha. This is the side of the triangle that is not connected to alpha. So this is opposite to angle alpha. This is adjacent to angle alpha. So if we took cos alpha, cos alpha will be adjacent, which is a over hypotenuse, which is p. So don't forget, a is the x component of the vector, and p is the magnitude of the vector. So from here we see that a, the x component of the vector, is given by p cos alpha. So that is that about that. The same thing happens, you can easily verify that the same thing happens if we consider the angle that the vector makes with the y-axis, angle beta. So looking at angle beta, we see that the length of this side is b, which is the magnitude of the y component, and this angle here is also 90 degrees. So this is the right angle, and so as far as angle beta is concerned, this is the side that is opposite, and b is the side that is adjacent to angle beta. So if we would take cos of beta, it follows that that will be adjacent, which is b over hypotenuse, which is still p. And in this case, this means that the components, the y component, will be given by p cos beta. All right. So that is the idea. So this cos alpha and cos beta are called the direction cosines of the vector p, because in this case they are the cosines of the angles that the vector makes with those axes. So the cosine of the angle that the vector makes with the positive x direction is called direction cosine, okay, in the x direction. So the direction cosine for the y-axis is given by cos beta, which is where beta is the angle that the vector makes with the positive y direction. Okay, so what if we add the vector here? If we add the vector here, what will be the difference? Then we'll see the angle that it makes with the positive x-axis will be given by this. And the angle that it makes with the y-axis will be given by this. Okay. So if we add some other vector, let's say the vector is here, for instance, the angle that it makes with this axis will be given by, the angle that it makes with the x-axis will be given by the positive x-axis, please. It has to be to the positive side. So the angle that this makes here with the y-axis is going to be directed this way to the positive side. So that is obviously above 90 degrees. Okay, so the direction cosine helps us capture whether the component is positive or negative, and so on and so forth. Okay, so that's how it works in the two-dimensional case. So in the three-dimensional case, we will have something similar. Just imagine that you have these drawn this way. We're mostly interested in the three-dimensional case anyways, but it's good that we already have an idea of what it should look like, okay, from the two-dimensional case already. And say this is again our x direction, and this is our y direction, and this is our z direction. So if we have some vector, okay, in space, then we can find out what angle does it make with the positive z direction. We call that gamma. The angle it makes with the positive y direction, we call that beta. And the angle it makes with the positive x direction, we call that alpha. Okay, so those are the angles, alpha, beta, and gamma. And this is still some vector P, for instance, that has magnitude or that has components A, B, C in the respective directions, like we illustrated in the last lesson. So if that is the case again, we will have the cosine similar to what we have up there. It will also follow. We can show that this is going to be given by cos alpha being equal to the x components, which is what we denote as a here, divided by the magnitude of the vector. And similarly, cos of beta will be given by the y components, okay, b, divided by the magnitude of the vector as well. And the cos of angle gamma, cos of gamma will be given by the z component, which is c, divided by the magnitude of the vector. So these are the direction cosines of the vector. So if we needed to find direction cosines, we just need to know the component of the vector. Once we have the component of the vector, we know the magnitude of the vector, then we are good to go. Okay, so of course, if we only know the magnitude of the vector, we know how to get the so if we only know the components of the vector, we know how to get its magnitude. So we have previously seen that P is magnitude of P and it is given by the root of a squared plus b squared plus c squared, where a, b, and c are the components in the x, y, and z directions respectively. So we could as well write this as cos alpha equals a over the root of a squared plus b squared plus c squared. Okay, so similar things can be written for this case as well. So we say that this is cos beta. It will also be equal to the square root of a b over the square root of a squared plus b squared plus c squared. And we can write the same thing for this and say that our cos gamma is equal to c over the square root of a squared plus b squared plus c squared. Okay, so this tells us how we can get the direction cosines of a vector. Okay, and so what is the usefulness of this? There are situations where we might want to. So let's before we look at that, please let us visualize this on the graph that we had. So this was the visualization we used earlier. So you should see you can actually play around with these. For instance, we only considered cases where the vector is directed this way. You can play around with the components. If we are going to have a negative component, for instance, this is a positive x component. So we're going to have a negative component. For instance, let's say minus 10. What will the implication of that be? So just press enter. You will see that negative component simply means that the vector will be directed opposite. So we can see that the x component, this is the x direction. This is the positive x direction. So negative x component means the vector will be facing the negative x side. So that's the negative x side that it is facing. Now this is positive x side. This is negative x side. So you can see for the others, it is still facing the positive y side here, as we can see here. This is the positive y side and it still faces that. Let us orient this way. So where the labels appear, okay, where the label appears here, that's the positive side. This is the positive side for y, this is the positive side for z. So you can see that this vector still has positive z components. You can see the z component here positive, the y component is positive, but the x component is now facing backward, which is negative. And the reason for that is because we change this to negative. Okay, and if we change this to negative as well, let's say minus n, this you can see that the vector is directed differently now. It's directed to the back here. So that's that about that. So basically what we're interested in for now is the angle that is mixed with each of these axes. So we can mark this so that it shows the angle. So the vector, you can see the vector right here and the angle is mixed with the x-axis. So yes, it becomes clearer here. This is the vector, and you just trace it out right here to the x-axis. So don't forget, this is the x-axis. So the angle mixed with the x-axis is this. So you can see in this case, it is an angle that is greater than 90 degrees because the angle always has to be traced to the positive side. So this is 128.6 because it has to be traced to the positive side. Okay. So you can also just undo that and visualize the angle it makes with the that is the y-axis. So we can visualize that as well. We rotate these. Let's get it back to our familiar view for now and see what it looks like. Yes, so this is it here. This is our y-axis, and this is the vector. The vector is facing that end. So coming to this side, it is still 128 is greater than 90 degrees because the component is negative. Okay. For the component that is positive, of course, we expect that it should give us an angle that is not up to that. So we can see it is not up to 90 degrees. This is 62.06 for the z component. For the angle it makes with the z-axis. So that's quite obvious from here. So this is the angle right here that it makes with the z-axis. So these are the angles that we have called alpha, beta, and gamma. So even though this visualization uses alpha, beta, and theta, okay, for us we call them alpha, beta, and gamma. All right. So that is the idea with the angle. It has to be traced to the positive side. Okay. And once you have that, then you have what we call the direction cosines of the vector p. Okay. So now we say that what is the relationship? We want to firstly establish what's the relationship between these angles. So one thing we know already is the fact that p, we know p is equal to the square root of a squared plus b squared plus c squared. And of course, that stems from the fact that p squared equals a squared plus b squared plus c squared. Okay, so we also know from here that we can write if we make this a, okay, if we make a the subject here, a will be equal to p cos alpha, b will be equal to p cos beta, and c will be equal to p cos gamma. So we can make that substitution here. So if we go ahead, we can simplify this further. Just leave everything in terms of p. A is equal to p cos alpha. So this is p cos alpha all squared. And this will be plus b. So from here we know b is equal to p cos beta. So this is going to be p cos beta all squared. Then plus c. We know c is p cos gamma. So this is p cos gamma all squared. And when we take the square of all of these to simplify this further, we see this is p squared equals, this will be p squared cos squared alpha plus p squared cos squared beta plus p squared cos squared gamma. So p squared is common to all of them, so we can just cross that out, divide through by p squared, we'll have all of these out. So from here we can see there's a relation between these angles. So we have cos squared alpha plus cos squared beta, okay, plus cos squared gamma to be equal to 1. So that's the relationship between the direction cosines of a vector. Okay, so if we, that means that if we know any two of them, let's say we know alpha and beta, we can get gamma using this relation. Okay, if we know beta and gamma, we can get alpha using this relation, and so on and so forth. Okay, so that is that about that. Now, one last thing to note here is that if we have two vectors, so for instance, if we need to get the angle between two vectors, we'll examine how this comes about as we proceed with this course. You see why this is correct. Okay, for now we will state it without proof. Okay, so the angle between two vectors. So if we have two vectors A and B, so let's say these are spatial vectors now, vectors in space, okay, so they are not necessarily confined to this plane, okay, even though we draw them in this plane. Let's say we have some vector A, let me not use A now, let's say we have some vector P and some other vector, say vector Q, and then we are interested in the angle between these two vectors, say angle theta between these two vectors. So we can say let L1, M1, and N1 be the direction cosines of vector P, and L2, M2, N2 be the direction cosines of vector Q. That is in the Cartesian coordinate system as we have learnt it now. Then it follows that the angle between them, or the cosine of the angle between them, so in this case we have called that angle theta, the angle between these two, is given by the products, the sum of these products, L1 L2 L1 L2 plus M1 M2 plus N1 N2. So if we want to get that angle theta, that means that our angle theta will be equal to the cos inverse of L1 L2 plus M1 M2 plus N1 N2. Okay, so this will give us the angle between the two vectors P and Q. Um, we will consider how this is reasonable, or why this is reasonable or correct, as we proceed with this course. For now, just take it as that. Okay, you'll see how it works as we proceed with the course. All right, so that is that about the direction cosines of a vector. So we now proceed with this chapter by considering a number of examples on the concepts we have discussed so far. So you see how we use this concept to solve actual problems, or what we can get, some information we can get from a vector using the concepts we have so far developed. Okay, thank you for watching. I'll see you in the next lesson.